This is a rattleback. It has a rather curious behavior that when spun in one direction, it reverses, while it's spun the other way, it simply rotates. This asymmetry can be traced to the fact that the shape of the bottom is not symmetric. It's higher on this side than it is on this. Let's see that again, close up. To understand the reversal, we will break the process down into 3 steps. First, when it rotates clockwise, the first thing you notice is that it oscillates about its short axis, in other words, like this. That can be explained mathematically, but the calculation is not easy. This is the only step which I will leave incomplete. The next step is based on energy conservation. Since the rattleback moves in such a way that the point of contact does not skid, the force applied to it does no work. Thus, energy is conserved. The initial amount of energy in the rattleback is given by this, 1/2. This is the moment of inertia about the vertical axis, about this axis. And n represents the angular velocity that it initially has. Now, as the oscillation grows, that is the rotation about this short axis, that takes up energy. The amount of energy it takes up is given here. It's 1/2 the moment of inertia now about this axis, times the angular frequency for the rocking motion, times the amplitude of that motion. Now, Lx is comparable to Lz. Omega sub x, the angular frequency for this, is quite high, certainly higher than n. The amplitude, that's the amplitude in radians, you expect to be something of maybe 0.1, 0.2. The final result is that this quantity, in fact, will be comparable to this. In other words, as the oscillation grows, it takes all of the initial energy. That means that the rattleback must
Hello, Djordje Romanic here. Today we have a very simple problem in which we need to investigate the importance of the Coriolis force in a tornado. The text of the problem is now on your screens. So the tornado in question is an EF0, and actually weak EF0 tornado. Characteristic velocity is only 30 meters per second. Tornado is at the latitude of 20 degrees and diameter of this twister is 100 meters. Does the Coriolis force matter? What does that even mean? Well, that means if we want to investigate dynamics of this tornado or kinematics, flow field, we want to do modeling, do we need to account for the Coriolis force? How do we approach questions like this? Well, we use the concept of the Rossby number. That's the plan.
Simple plan.
Now, from my previous videos, I hope you know that a Rossby number is defined as U over FL, where U is characteristic velocity in a given phenomena, L is characteristic length, and F is Coriolis parameter defined as 2 omega sine phi, where omega is angular velocity of the Earth, 7.3 times 10 to power negative 5 second minus 1, and phi is latitude, which in this case is positive number because it's northern hemisphere. All these are of course explained separately in my previous videos. So if you calculate this, I believe you will get that this is approximately 5 times 10 to power negative 5 second minus 1. So that's the Coriolis parameter or Coriolis frequency. Characteristic length of this tornado is diameter 100 meters and characteristic velocity is 30 meters per second. So before we plug in numbers, what do we need to know? Well, we need to know that Rossby number represents the ratio of the Coriolis force and or of inertial forces and the Coriolis force. If the Rossby number is very, very large, then the inertial forces dominate the flow field and Coriolis force is not so important. If the Rossby number is order of magnitude of 1 or around 1, then the Coriolis force is equally important, of equal strength, as the inertial forces. And if the Rossby number is below 1, which can happen often in oceanography, then Coriolis force is even more dominant than the inertial forces. So when we get a result, judging on the value of this number, we can answer this question: does the rotation of the Earth matter? So this is equal, U is 30 meters per second, F is 5 times 10 to power negative 5 second minus 1. Everything is in SI units, so I don't put units over there. And times characteristic length is 100 meters. Now, I believe if you calculate this over here, you will get a value that is approximately 6,000. And 6,000 in my books is much larger than 1, which means that the Coriolis force is completely not important in this tornado. So to answer this question, the answer is no. Coriolis force does not play important role in the dynamics and kinematics of the flow field in this weak EF0 tornado. Now part B, that was part A. Part B of this problem says what would have to be velocity in this tornado so that the Coriolis force matters. Well, we can solve part B here. So we just go back to the definition of the Rossby number. We can say if the Rossby number is order of magnitude 1, that means that the Coriolis force is equally important as the inertial forces. And now, taking this order of magnitude value, we can find u that satisfies that value over here. So, namely, if we say that 1, and that's Rossby number, is equal unknown u divided by known f and l, and f is approximately 5 times 10 to power negative 5, and L is 100. From here, it follows, if you calculate these, that U needs to be around 5 millimeters per second. So you can see that the velocity in this vortex would have to be around, because this is order of magnitude, around 1 millimeter to 5 millimeters per second for the Coriolis force to be equally important as the inertial forces. Or, in a different words, we could say that this is the value of the velocity that needs to be in this vortex so that the rotation of the Earth plays important role in the dynamics of this tornado. Clearly, this is extremely weak velocity, 5 millimeters per second. That's a velocity we cannot even detect with our body. You cannot detect velocity of 5 millimeters per second. And therefore, clearly, this wouldn't even be tornado. It would be just some weak vortex with this velocity that would be undetectable by our senses, except if we put some instruments over there. At any rate, what is important is for you to understand how to tackle these types of questions. If the question says, does the Coriolis force matter in some natural phenomena, then your first approach to solve that question should be to use Rossby number. If the Rossby number is very large, Coriolis force doesn't matter. If it is around 1 or below, then it does matter, and you have to account for it. Until next video, goodbye. Hello, Djordje Romanic here again. Today we have a very interesting problem. We are starting to mix different disciplines in physics and atmospheric sciences, physics in general. Problem, you can see it now on your screens. Okay, now notice something, that indeed this magnetic force looks quite similar to Coriolis force up to these constants Q and 2m. Okay, so we need this force to balance this force. Well, that means that Q V cross B needs to be equal but opposite of this. So this is Coriolis force minus 2m omega cross V, and this force needs to be equal to that but opposite. Okay. I can write this as Q V cross B is equal minus and minus will give me plus, but I will again put minus, and you will see why, because I want to reverse this cross product. And now look, this cross product indeed looks like this cross product over here. Therefore, omega as a vector needs to be negative q times b divided by 2m. So, if I introduce non-inertial reference frame that has this angular velocity, the effect of this magnetic force over here will disappear if I measure them in that non-inertial reference frame. Well, Q and 2m are some constants, so we can see that omega needs to be, is proportional, let's say, to negative b. So that means if b was into the page, in this case, I have to introduce omega that is out of the page, and we usually use this to denote it. Well, I shouldn't use 2. I have to use omega, I have to introduce omega that is out of the page. And out of the page omega means counterclockwise rotation. Now, let's see if that makes sense. V cross B. V cross B. B is into the page. V cross B, my thumb is pointing in this direction. So that would be direction of magnetic force to the left of this motion. Now, what would be the direction of Coriolis force? Namely, where is it? Here. Omega cross V. Omega cross V would be like this in the same direction. So you might say, oh my God, you did mistake, but I didn't, because there is this minus over here. So omega cross V would be in this direction, but because of minus, it will go in that direction. So Coriolis force, in other words, Coriolis force would tend to deviate this towards the right, and magnetic force would tend to deviate this motion towards the left. If these two are the same, and they will be the same under this condition, then the effect disappears. Of course, it just disappears as a fictitious apparent process because we are introducing this non-inertial reference frame. Until next video, goodbye. Hello, today we will talk about Navier-Stokes equations. Finally, after several months of introducing different forces in our talk, we are ready to cast the most important equations in fluid dynamics, atmospheric sciences, and oceanography, the Navier-Stokes equations. So now, when we know all the forces that are acting on a parcel of air, namely we introduced them in previous videos, and we have real forces, pressure gradient force, gravitational force, viscous forces, and we have three apparent forces. That would be centrifugal force, Coriolis force, and Euler force. But we said Euler force, nobody cares about it, because the angular velocity of Earth is constant, so we end up with these 5 forces. What we need to do now is to put down these forces in quantitative form and cast finally Navier-Stokes equations. Let's do it. The acceleration du dt is equal to first pressure gradient force, second gravity, third viscous forces, fourth centrifugal force. And finally, fifth, Coriolis force. Here, u is a vector of velocity measured in respect to Earth's surface, which is non-inertial frame of reference. Rho is density, t is time, p is pressure, g is gravitational acceleration in vector form, nu is kinematic viscosity, omega is angular velocity of the Earth, and r is the radius of the Earth. This is Navier-Stokes equation in vector form in non-inertial frame of reference. In an inertial frame of reference, the two apparent forces disappear, and we end up only with these three terms on the right side. If we also neglect viscosity, then the pressure gradient force and gravity, together with acceleration, that's called Euler equation. So Euler equation is the special case of Navier-Stokes equation when there is no viscosity and there are no apparent forces. This is a vector equation. Since we have 3 dimensions of space, this represents 3 equations in scalar form.